Since the beginning of time, good and bad bacteria have coexisted in the intestines of animals and humans in an uneasy truce. Control of the bad bacteria, called pathogens, is critical since they can cause sickness, reduce animal performance, and even result in death. Pathogens anchor to the specific sugars on the surface of the stomach and then multiply and produce toxins. This results in damage to the intestinal structures. Peering through the mucin cloud which shrouds the intestine, the resulting destruction may be seen. The concentration of pathogens on the ends of the villi eventually causes pieces to break off. The villi in turn respond by releasing more mucin in an attempt to wash away the invaders, but usually this only results in less nutrients being absorbed. In the 1950s, animal producers discovered that feeding low levels of antibiotics in feed could control the pathogen numbers, and this practice continues in some markets today. However, antibiotics are not selective and can also kill beneficial bacteria. Bacteria also adapt to their environment rapidly with continuous exposure to antibiotics, leading to the development of resistance. Bacteria easily pass resistance genes between each other, with resistant bacteria taking the place of the ones that the antibiotic removes. This mechanism is similar to the one that allows pathogenic bacteria to anchor to the sugar structures on the villi. Once anchored, the resistant genes, called plasmids, transfer across the link, making both bacteria resistant. This leads to serious health concerns for both animals and humans. 10 years ago, researchers in the United States made a breakthrough. By borrowing a trick from nature, they found a brilliant and elegant solution. These scientists from the company Alltech discovered a method to release specific complexes from yeast that mimicked the sugars to which pathogens attach. Commercially known as biomass, this is now included at low levels in animal feed. In the intestine, biomass acts as a decoy by attracting pathogens that attach to sugars on its surface rather than the villi surface. Once immobilized, the bacteria are harmlessly removed. Eliminating pathogens naturally brings mucin production back to normal, leading to a healthy villi surface. Animals fed biomass absorb nutrients more easily, get fewer diarrheas, and perform better. In addition, biomass can block the passing of antibiotic resistance between bacteria. This means that antibiotics work better when animals are sick and really need them. Biomass also improves immune function by bundling the pathogens it has found in the intestine and presenting them as a package to dendritic cells. These dendritic cells reach out from below the intestinal wall to capture material floating around in the fluid of the stomach. They digest the package of pathogenic cells and present pieces to what are called T cells. Then there are microfold cells, also called M cells, located in areas known as Peyer's patches. These can also capture biomass. Upon entry into the M cell, the biomass molecule with pathogens attached will be met by a macrophage. Macrophages do the same job as dendritic cells by digesting, then presenting the pieces on their surface to the same T cells. T cells that come in contact with macrophages or dendritic cells become active, and the T cells then send out signals called cytokines. These cytokines are absorbed by B cells, activating them in turn. These activated B cells move back into the surrounding tissue and secrete immunoglobulins, the immune system's first line of defense. Biomass increases the efficiency of the immune response by forewarning the immune system of the presence of specific pathogens and their families. Immunoglobulins produced in this way become concentrated in the villi surface, the mucus layer, and intestinal fluid, ready to help fight infections before they become a problem.